Micromechanics of Composites. And once we discuss all these topics, we will finally conclude the learning drawn from the interactive session. So in the last live session, we started by discussing about petrographic analysis, in which powdered samples of concrete are collected from sites and analyzed under high power microscopy or other sophisticated instruments. We saw examples like ICP, AES, XRD, and TGA, and different microscopies and their application. Then we discussed and their applications, like for finding void content or properties of interface or cracking in concrete due to different kinds of chemical reactions that can occur due to environmental aggressive ions. Then we discussed about load testing of concrete structure. In simple terms, it is nothing but keeping load on the structure and checking deflection. In this, we talked about when load testing is needed, how load is calculated, uh, how to conduct testing, either monotonic or cyclic loading, and how to interpret result. And we also saw images of like load testing and monitoring for at different locations. And then we started our discussion about on repair and retrofitting. We first understood what each term mean and how they are related to performance and deterioration. Then we saw a flow chart of different steps of a concrete structure inspection and different parameters which help us to decide whether we need to go for repair or retrofitting. So these are the parameters that we saw. After this, once we are clear whether repair is needed or retrofitting, we understood what is the procedure ahead. Okay. So once the choice between repair and retrofitting is done, the first step is to prepare the existing structure, in which we discussed shoring, scaffolding, and conditioning. Once my structure is ready for action, we talked about different types of repair materials followed by grouting and its types. Now, when grouting is needed to be carried out, we talked about different ways in which grouting can be done. Here we talked about drilling and plowing, routing and sealing, pre-packed aggregate, and stitching and stapling methods. Okay. Uh, for each method, we saw their desirable application areas. Then we talked about another way of surface integration repair through shotcreting, in which we talked about both dry mix and wet mix shotcreting and their application differences. And finally, we talked about ferro cementing and its application. Okay. After this, in locations where critical corrosion damage has occurred to reinforcement or exposure condition is severe, we discussed about different ways in which corrosion can be controlled. Starting with electrochemical methods like cathodic protection through SCCP and ICCP, and electrochemical realkalization and electrochemical chloride removal. We also talked about use of corrosion inhibitors, and we also talked about use of coated reinforcement. So this was all from the last session. Now we know that when we need to evaluate a structure or if it requires repair, what needs to be done. But what if the structure's functionality is changed and now the structure is demanding to have more strength? In such cases, retrofitting is done. So, in simple terms, retrofitting is nothing but enhancing the capacity of a structure over its original design. This can be accomplished in three ways, either by replacing there's a poor quality aggregate and defective materials by a better quality material, attaching additional load bearing members or material over the structure, and redistributing the load that is acting on the structure to reduce the load acting on the structure and distribute it properly within the structure. Okay. Now, when we talk about replacing, it can be accomplished by using high quality concrete. So it is clear that the old grade concrete has been replaced by an high quality concrete, and it will enhance it will strengthen the structure. Okay. as it will increase the compressive strength of the concrete, which will provide it more load bearing capacity. Okay, but for attaching and distribution, we can go for like this is what we talked right now. Okay, high quality concrete. Okay, but for attaching and distribution, we can go for different types of materials like reinforcement steel bar, thin plates, straps and tendons, and fiber reinforced polymer composite. Okay, so we will see the other three over time one by one. Now, there are different ways in which the previously discussed materials and or members are used in retrofitting. Some of the conventional ways to carry out retrofitting include section enlargement. Okay, so in this, what section enlargement means, it is basically addition of new concrete or reinforcing steel over the existing surface, and it is done to enhance the strength and stability of a structure. And it is a very commonly used retrofitting repair technique in residential buildings, bridges, and historical buildings. So you can see here one example of how a building is like repaired by section enlargement for from all the sides. Okay. Second method can be composite construction. This involves placing additional plates and structural elements on the existing structure. This is done to increase the stiffness and load carrying capacity. And the load transfer between existing structure and composite is aided using adhesives, grout, and mechanical anchors. So you can see here FRP confinement has been applied on columns to strengthen the structure, and here also you can see, FRP composites are applied at the base to strengthen the structure. Okay, we'll see this much detail about FRP later on also. Third can be post tensioning. So this involves placing tension bearing compounds like steel plates, rods, tendons, and strands. Can be either internally within the member or externally to the member by jacketing. Okay, so it can be internal or external both. And what post tensioning does, it relieves overstressing and reduces the reflection caused by bending and buckling. So here you can see post tensioning steel bars have been placed at the deck of a bridge, and here these are post tensioning stand that are placed inside a bridge girder. Okay. And final method is stress reduction, which can be accomplished by cutting expansion joint, jacking displaced structure, installing isolated bearing, and removing certain portions of the structure. And this is done to relieve the stress within the structure. So here you can see one example how the distress that was caused in the pavement slab was relieved by introducing grouting material within it. So we will see this in detail. This is known as slab jacking, and we'll see later on about this. Now, the part of crack filling through grouting is clear to us from the last session. Okay, whenever strengthening is applied on a structure, the first basic thing is to first repair the existing cracks on the structure. And common way is to use the grouting method. Okay. However, there is an additional thing to remember here. In case of crack filling, suppose we have a beam. Now, if possible, the crack shall not be grouted during summers. Okay. So we know grouting, internal grouting through pressure injection, and external grouting. Both we have talked in detail in the last lecture. So when there is grouting application on site, we need to take care about the temperature and the condition of the structure also. Suppose I have a beam which is cracked from the center. Okay. Now I want to grout the crack, okay, before applying any strengthening technique or something. So if possible, the grouting should not be done in the summers. Why? Because in summer, what will happen? There will be expansion. Okay, so this will expand. Okay, this will expand. So what will happen? My crack width will decrease. Okay, so this was my crack width. It will come to very small quantity. Okay, now if I am grouting the material inside this crack, when the winter will come, it will again contract. Okay, when it will contract, it will exert tension on this grout material in between, and there can be additional crack, okay, near the existing crack that may occur. So that's why it is suggested that when grouting or some application is done for crack filling, it should be done in winters. Why? Because in winter there will be contraction. Okay, so my crack will expand. Now my crack has expanded. I am grouting the crack. Okay, so in summer, when again the expansion of grouting, concrete member will occur, what will happen? This grouting material uh, will like will experience contraction, and it will be able to resist the compression well, rather than resisting the tension. Okay, so when to do crack treatment is also important. We earlier saw high quality concreting as retrofitting material. Okay, now let's talk about steel as retrofitting material. So, steel is used as a retrofitting material in mainly two ways: as an additional reinforcement, either longitudinal or transverse, to provide additional load bearing capacity to the structure. Additionally, it can be used as plates, straps, and tendons also for strengthening the connection or for external support. Okay. So the important thing in all the cases is attaching the steel to the concrete, and that shall be done properly so that the load transfer is not affected, and thus for attaching steel to concrete, it is done either in three ways: either through mechanical connection or adhesive connections, or both. So mechanical connection includes anchor bolting, and adhesive connection includes ways like epoxy resins. And sometimes we can go for both, the combined combination of both. The same can be seen in the images also, where which shows different combinations of connection. Like in the first image, you can see this is a steel plate and this is a concrete substrate, and it is connected by a anchor bolt. Okay, here you can see the steel plate and the anchor bolt along with resin both are used for connecting the steel plate to the concrete substrate. Here you can see just on the surface the steel plate is applied using epoxy adhesive, and here you can see on the surface also epoxy adhesive is applied, and in the it is used as a grouting material also with the anchor bolt. So there can be different ways in which we can connect steel to the as a retrofitting member, and this is very important because it will dictate how properly the load transfer is occurring from concrete to steel. Because suppose we are placing a steel on the surface to take load, but it is the load transfer is not occurring properly between concrete and steel, then there is no use of using that as a retrofitting material. Okay, additionally you can see through bolting can also be done in places where there is a deep crack for like connecting the steel to the existing member. Okay, so the important thing with attachment is it should permit load transfer, and thus it is a very important step. Now, since we have developed a general understand background about retrofitting and different ways of retrofitting, let's dig deep into the discussion of how and what type of retrofitting can be done for different requirements, for different elements of a structure. Here, by different requirements, we mean sometimes the fractional strength needs to be enhanced, while sometimes it's the shear capacity or maybe joint movement capacity. So, for each of such demand, different actions can be taken. Okay, so first we'll see a retrofitting of beams and girders, in which the first we'll talk about shear strengthening. Okay, when I am observing shear cracking on the structure and my shear strength of the structure is needed to be strengthened. Okay, now one way to do this is by using post tensioning, either internally or externally. Okay. Internal post tensioning is done by drilling through the concrete member and capturing the areas of distress and installing steel tendons and filling epoxy grouting in the leftover spaces of the drill and locking the end by the anchor bolt. So in this you can see a girder in which through the girder element, a hole was drilled, steel rebar was inserted, the space between the concrete and the steel tendon was filled with a grouting material, and the end was anchored. Okay, so this is internal post tensioning. Okay, now while in external post tensioning, only a small portion of member is drilled, while the remaining method is the same. So you can see here only a small portion of the member was drilled, and the remaining member was as it is, and steel tendon was inserted. Okay. While in this second image, we can see external post tensioning being carried out after filling the existing crack with the epoxy grouting. So this was a shear crack. Okay, This crack was first filled with an epoxy grouting, and then through the beam and the external support, a post tensioning rod were installed and it was anchored from the ends. Okay. Another way of shear strengthening can be providing additional steel reinforcement. So, in the first image, we can see shear cracks on the girders. So, here you can see shear cracks are present on the girders. These are arrested how? By drilling holes perpendicular. So, in this image, you can see holes are drilled perpendicular. Okay, and then steel reinforcement was inserted in these hole along with the grouting material. Okay, while in the second image, external steel plate bars are used to arrest shear cracks, which were also epoxy grouted first. So in this, you can see near the supports there are like at 45-degree angle shear cracking was observed. So what was done? Steel plates were used, and externally it was attached to the surface. After the cracks are filled with the grouting material. So this is the diagram in which you can see how it was occurred, and in real life also you can see how it looks. Okay, so such a steel addition of steel reinforcement near the joints are done to to arrest the shear cracks and to strengthen the structure for shear strength. Okay, here you also at the bridge deck you can see steel plates is horizontal steel plates is installed for strengthening the steel. Okay, against shear force. After shear strengthening, the second is flexural strengthening. Okay, by flexural strengthening, we mean to increase the bending moment capacity of a beam or girder. Okay, so if we revisit the basics of beam design that one must have seen in the design of our reinforced concrete as per IS 456, the bending moment of resistance of beam is given by mu limiting. So we write moment of resistance of beam as mu limiting, and it is directly proportional to the area of steel AST and the square of depth. Okay, area of steel AST and d square. Okay, so we like what is the equation for this? So I will write that equation also. So we like this: m is equal to 0.36 fck d square plus either this, or we write m is equal to 0.87 fy ast. So in both this equation, you can see the moment of resistance of beam for flexure for bending is directly proportional to the area of cross section, the width of the member, the depth, square of depth of the member, or area of steel that can be provided. Okay, so now if one can remember this, one can easily identify what all ways are possible for retrofitting a beam for flexural strengthening. Okay, so just remembering this two equation, let's see different methods one by one. The first one is providing concrete overlay or section enlargement. Okay, what this will do? This will increase either width or depth or both, and since B or D will increase, the limiting moment of resistance of the member will increase, and it will be able to take more load. Okay, so in the first diagram, we can see both methods are depicted. So over the existing beam, concrete overlay is provided, which is provided on both the side. Okay, on one side it is provided, which is increasing the depth. Okay, and here concrete overlay is provided on both the side, which is increasing both width and the depth of the member. So this is section enlargement and this is providing concrete overlay. Okay. Now the CP WD Handbook of Repair and Retrofitting also shows clear diagram of such methods. So in the first diagram, section enlargement is done on the underlying beam. uh, so here you can see there is a T beam. So here this is the old concrete. Okay, this is the boundary of my existing structure, and over it additional concrete was provided with steel tendons to like strengthen the existing beam. Okay. While in the second diagram, the T beam, a combination of both beam and sail, was retrofitted from both top and bottom. Okay, so here you can see at the top also concrete overlay was provided, and at the base also section enlargement was done. Okay, and just to ensure that the old concrete is connected well with the new concrete, the enforcement was run throughout the old and the new concrete. Okay, another way.
Sir, there's a doubt in the previous slide, sir.
Okay, ask.
Sir, in this beam section enlargement in the right hand side on the top, what you're showing, sir,
Yeah.
the four reinforcement which have been provided additional.
Yes.
How are we planning to tie them up, sir? Because generally the old one we have the stirrups where oblique the confinement reinforcement what is binding all those five steel reinforcement.
Okay.
But how about these four which are at the base?
So you can see here also stirrup is provided, no, this one. And this stirrup is running till the inside the old concrete. So this is my boundary of old concrete. This is my new concrete. This is my new stirrup which is running inside the old stirrup.
But sir, generally we talk about having this complete in a square shape and having that angle of 135 degrees so that
So maybe here also they have not depicted that angle properly. They just wanted to show that the encasement is done. Here also some bending will be done to ensure that the stirrup are properly interlocked with the old concrete.
okay, sir. And in the combination slab and beam overlay, sir,
Hmm.
what we are talking is like we are putting this top concrete, what you're saying, overlay of concrete on the top
And at
of
the
the
bottom also we are doing the section
bottom.
enlargement.
Yes, a bottom as it is exposed, so we can have that U shape of thing of the foam work and fill this concrete and the steel, sir. It will support it.
Okay.
But how about this top overlay? Because the beam is already embedded into the slab.
This top overlay is for the slab, na, not for the beam.
But sir, this reinforcement that we are providing for the beam only, na, sir. The
This
two.
reinforcement is the additional reinforcement. Suppose there is a lot of bending moment that is acting on the beam. So we have talked like in design using IS 456, you must have seen doubly reinforced columns are also there. Now, suppose just the section enlargement from the base, it won't be able to like match the increased bending moment. So I need to provide some reinforcement at the top also. So that's why when at the top also concrete overlay is done, and here also at the top some reinforcement is provided and it is anchored with the old concrete.
But sir, aren't we increasing the AST more, sir? Because already, if you see, already 5 bars were there as per the
Uh,
exact design.
so we want to increase AST na, because we want to strengthen the flexure capacity of the structure.
Now, sir, in this only, sorry, sir, because I'm asking few doubts.
No
Basically,
problem.
in this, sir, the slab. Now, if you see this beam, sir, combination of slab and beam overlay only.
Okay.
Now, this beam which is there in the center, and there's a slab on top of it.
Okay.
Now, this two top reinforcement for let us consider now this new steel which is going to come, that is 2 bars on top and 4 bars at the bottom.
Yeah.
Now, these 2 bars are on the slab,
Okay.
and these four are at the base of the beam.
Hmm.
Now, how do we put this confinement reinforcement? That is the shear, this thing all around this thing, sir. We how do we drill it,
So it is basically like drilling at the top. This is my old concrete surface, right?
sir?
So before applying the new concrete, I will drill some portion in the old concrete. I will first place the steel cage and then I will do the concreting from the top.
Then aren't we damaging the entire concrete
That
slab, which
is
is,
that is why we are doing strengthening, na. We are
sir?
retrofitting the structure, so we will damage the structure because we need to enhance its properties. If we are going for repair, it is generally on the surface mainly. But when we are talking about retrofitting, we need to take some measures without damaging, increasing strength and everything. It is not always possible, right?
Okay, sir.
Okay, retrofitting demands some destruction. You will see in the head slides also there are in several techniques there will be some destruction to the old concrete because we want to bind the new concrete or new material properly.
Sir.
Okay, so
Okay, sir.
there is one more image here. which you can see. So here in this image also you can see at the top some overlay was provided if I want to strengthen the top only, and at the bottom some overlay was provided if I want to strengthen the bottom only. And in addition to the reinforcement, there is stirrups also, which are like turning in the old concrete and binding the new concrete and the old concrete. Okay, so like this is a front view, that's why it is not very clear, but these are all like steel tendons. Like you will see ahead some examples of how these things happen.
Okay, sir.
Okay. Another way of flexural strengthening is by using externally bonded steel plates. Okay. Either through and through, okay, or on the one side only to increase the flexural capacity. Okay. So here you can see in the images there is through and through bolting. Okay, and the steel plates are attached at the top because near the joints my tension zone as is at the top, so that's why here the steel plates are attached at the top. However, in the midspan my tension zone it is at the base, so here you can see the steel plate was attached at the base. Okay, and here you can see bolting and grouting was done to attach the steel plate also. Okay. In some cases, if there is some deflection in the member also, then the steel plate is used and anchored with the bolt to reduce that deflection and increase the load carrying capacity of the member. So here you can see there was some deflection that occurred. Now lifting of the deflected slab was done by installing the steel plate and bolting it with the old concrete. Okay. And the CPWD handbook diagram also shows these methods. So in part A, flexural strength in the tension zone. Okay, so at the top near the support and at the bottom near the midspan was done from sides also, and from side also some plates were installed to take care of shear capacity. And here in the second image you can see just shear capacity was enhanced by placing the plates on the sides. Okay, now the next way of flexural strengthening can be externally post tensioning. So similar to how we saw in shear strengthening, here tendons are provided externally along the length of the beam. In tension side, that will provide additional resistance for flexure. We can see in the diagram two arrangement of such steel tendons, and also in the images their field applications. So here you can see in one diagram steel tendons were installed at the side, okay, to carry the flexure load, while here in case of continuous member the steel tendons were mounted at the top to the side. Okay, so it can carry the flexural strength near the support at the top and flexure strength at near the base at the bottom at the midspan. Okay, and these are the images showing both the methods in application. Okay. Next we can be by near surface mounting. Okay. So in this method, what is done? A small groove is made at the top of the beam, and the steel tendons or rebars are installed inside the groove. The groove is then grouted and sealed, and in this way, additional member will add value to the existing member by acting as an additional RC member to carry the tensile load coming from the top, which will be delivered to existing RC in its top fiber, which will be having a higher compression strength to resist the stress. So here you can see there is a concrete beam. So at the top of the concrete beam, a groove is made, and inside that groove, the steel rod of uh, or my steel tendon, anything is installed. So here you can see post tensioning was done. Okay, and then I will grout the material from the top. So why this is a popular method? Because it will be more uh, uh, pleasant looking, because repair is done and it is then grouted from the top, so it won't be visible, but the repair has been accomplished. Okay, so what such methods look like? So this is the front from the front view how they appear, and from the side you can see groove was made, an FRP rod was inserted, and an adhesive was sprayed. So this is a like a small RC member within a big RC member. So this will also carry load, this will also carry load, and this will strengthen the structure. So it can be a like small, the dimension can be as per the requirement. It can be a more vertical and more horizontal both. Okay. And another way is, till now we talked about how the moment of resistance of a beam can be increased. Okay, either by providing additional steel, or by increasing the width of the member, or by increasing the depth of the member. But there is one more way in which strengthening, flexural strengthening can be done. That is by decreasing the bending moment acting on the beam. So if we see a simply supported beam having uniform distributed load, so suppose this is a simply supported beam and there was a uniformly distributed load on this beam. So we say maximum bending will occur at the midspan, and it is like something like WL square by 8 or 64 or something. Okay, it is directly proportional to the length, span length. Okay, now if I will decrease the span length, my bending moment will decrease and it will strengthen by structure. So how it can be done? So since we can't decrease W because that weight is what it is increasing, we can decrease the span length. How? By shortening the distance between the support, and this can be done either by providing additional support. So here you can see these were old support, and in between additional support was provided. So initially my span length was L1, now my span length is L2. Since L2 is smaller than L1, my bending moment acting on the beam will be lower. Okay, and this will help me to strengthen the structure. Okay. Or what can be done? Some like knee braces can be provided from the base to the at some angle till the beam, and this will decrease the span length. So this is my new span length, and this was my old span length. Okay, so this will be my critical area where the bending will occur, rather than here where initially it was this. Okay. I hope everyone is clear with different ways of beam strengthening in shear and flexure. Any doubt in this part? Just remember those equation, basic equation of IS 456, and you will be able to understand what we are doing. Okay. Now, in case of wall, especially retaining walls where soil pressure may increase over time and may demand retrofitting, there are ways to strengthen the wall. The first is by providing new concrete shear wall or existing shear wall as shown in the figure. Okay. So remember here, it's not just providing new wall that will do our work. The load transfer between old wall and new wall is also important, and for that shear ankles are provided. So here you can see the new walls are provided, and along with this new wall, this is my longitudinal reinforcement running along the new wall, and this is my transfer reinforcement. So this is like this shear collar like pattern, okay, which runs inside the old concrete and it locks the new concrete with the old concrete, so that when the load is acting on the structure, it is properly transferring between the two. Okay, so it is very important that when I'm placing a new concrete overlay over my old concrete, the both the concrete shall be connected properly. Okay. uh, so this is one way. Apart from this, steel anchoring across the top and the bottom slab can also be done uh, to resist the buckling. So here you can see steel wedges are provided on the surface where the cracking was observed, and it was connected with the old concrete using epoxy grouting or diaphragm material for properly transferring the load between the concrete and the new steel members. Okay. So a buckling retaining wall can be strengthened either by attaching steel frames through the slabs or by using concrete overlay. Okay. After beams, which cover slab also and walls, we have columns. Okay. And so for columns, the demand of strengthening can come for four major reasons: either to resist the increasing axial stress, or to provide ductility for resisting bending stresses with minimum deflection, or for shear strengthening near support, or for moment strengthening near support. Okay. So let's understand each of them now. Okay. So first is axial strengthening. Now, axial strengthening is nothing but the ability to resist higher amount of axial load. So, if we recall IS 456 design of columns, the axial strength of column is given by. So, I will write that equation once. So, my axial strength of column, how I write, PU is equal to 0.4 FCK AC plus 0.67 FY ASC. So here AC is my area of concrete, ASC my area of steel under compression. So either by increasing AC, that is the area of concrete, or by increasing the ASC, that is the area of steel under compression, I can increase the load carrying capacity, the axial strength of the concrete. Okay. So how to do this? How to increase the area of concrete? This can be accomplished by section enlargement. So here you can see in the first image. Okay. In this diagram, you can see there was an existing column, and over that, a new concrete overlay has been provided along with its own reinforcement, and both of them were attached by through and through bolting. Okay, using a epoxy rod. Okay, so this was the front view, and this is the top view. Okay, so what this will do, it will provide me additional steel in compression also, and additional area of concrete also, which will increase my PU. Okay, so here you can see either from the side, one side, or from all the sides. New concrete overlay can be provided with these are my longitudinal bars, and this is my uh, 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 st- uh, stirrups. Okay, which is binding by longitudinal bar, and also some collars may be provided with the old concrete for properly locking the old concrete and the new concrete. Okay, so this was from all side, and this is from three sides if I want to provide. Okay. So the in the CPW handbook of repair and retrofitting also we can see the same thing. So we can see the concrete jacketing was done from one side to increase the area of concrete, and here you can see the person who asked me the doubt. Now here you can see shear key was used to connect old concrete with the new concrete properly. So in this diagram, it is clearly shown how new concrete and old concrete are properly connected for load transfer. Okay, so these shear keys are placed for connecting both the concrete members. Okay, so while in the second diagram, you can see taken from CPWD only, we have a multi-story building. Now, as per CPWD guidelines, even if one floor columns need to be strengthened, first temporary support shall be provided from bottom to top in a single line. So here you can see in a single line temporary supports are provided. Okay, then section enlargement shall be carried out from bottom to top. If my all the columns require section enlargement, then from C1, C2, C3, and C4, like this, I need to go for section enlargement. Once my retrofitting repair is done, then I can remove the support from top to bottom. So there is a sequence of activities. So in this points here also you can see sequence in which the activity is carried out. First we will provide support, then we'll carry out the retrofitting, and then we'll remove the support. And in which order support shall be provided, in which order retrofitting should be done, and in which order the support shall be removed, it is clearly mentioned in the handbook. Okay, so this was axial strengthening, either by increasing the area of concrete or by adding new steel in compression. Okay, now for ductility strengthening, we mean improving the bending moment capacity of the member to tackle buckling or bulging. So, as per IS 456 design of columns, the greater is the area of longitudinal steel, higher is the bending moment or resistance, and better is the ductility. So, this can be accomplished by RC jacketing. How? Simple, by adding a longitudinal reinforcement attached to old concrete by epoxy, adding stirrup to enclose the new cage, connecting these new stirrup with old concrete column, and then at last concreting the cage from the top, either using conventional concreting or after placing formwork, or by using shotcreting if possible. Okay, so here in the image also you can see there was a old concrete above old concrete, the steel cage with the longitudinal reinforcement was provided. Okay, in addition to that, the stirrups transverse reinforcement was installed everywhere around. Okay, it will run through the concrete also, and it will enclose the steel cage also. And then from the top I can do the concreting either by placing formwork and doing some conventional concreting, or by, if my stirrups are very small in diameter and they are attached to the concrete surface, I can also use shotcreting method. Okay, so in the image also you can see how RC jacketing is being carried out here and here. Here you can see steel plate was directly attached to the existing concrete column using epoxy as a adhesive. Okay. While in shear and moment strengthening, first for shear strengthening, shear can be critical near the supports that we know, where punching shear can occur due to inadequate shear capacity of the connection. Now, how to tackle this? Either this can be done by increasing the section area near the joint using shear collar, as shown in the first diagram. What this does, it reduces the shear stress by increasing the area of shear transfer. Okay, by providing additional steel near the joint, what will happen? There will be more area for shear transfer. Okay, more area of steel to accomplish the shear transfer, and thus shear cracking risks will be lower. Now, this collar shall be properly attached using non-shrinking route for effective load transfer. Okay, so here you can see in this image, non-shrinking route was used to properly attach the this shear key with the old existing joint of column beam and slab, column and slab. Okay, while moment strengthening is required generally at beam column junction. Okay, and this can be accomplished either by using steel plates over the column near the joint. Okay, so you can see here steel plates are connected near the joint, okay, over the column, or by using steel plates which are connecting both beams and the columns. Okay, so these are like triangular plate, so this will connect beam also and it will connect columns also. So through columns also it will connect, and through beam also it will connect, and it will like a kind of steel jacketing near the supports. Okay, so this is one way in which moment strengthening can be done near the support, or other way is to provide a shear wall. Okay, so between columns and beam I will cast a shear wall, and which will be acting as an additional member to carry the shear stress. So instead of load transferring here, it will transfer to the wall also, and it will reduce the load on the column. Okay, I hope the discussion about column strengthening is clear. Any doubts? Any doubts till in the discussion till here? Okay, so let's see ahead. So these are like very basic repair retrofitting technique. If you remember how, what is axial strengthening, what how axial load is acting on a member, you can yourself think what is the repair which is suitable. So the important thing is to identify which issue I need to address and how to address. Okay, once you identify what is the issue, whether ductility is the issue or axial strength is the issue, or the capacity near the joints are the issue. Once you identify the issue, the repair technique are all common. So initially we saw those 4 or 5 techniques. Huh? Those are the only 4 or 5 techniques that we are discussing for different members again and again. Okay. So till now we talked about strengthening of structural member above ground. Okay, columns, beams, walls. Okay, and slabs. Okay, let's talk about strengthening of foundation now. So, if we recall our discussion from basics of structural engineering, the load is transferred from slabs to beams to columns and then to foundation. Okay, which then transfers the load to the underneath soil. Now, when there is a functionality change of the structure, the total load on the foundation will increase. So, strengthening of foundation can be done in two ways: either by increasing the bearing capacity of the soil by improve by like soil consolidation, or by increasing the area of cross section of footing so that it can accommodate more stress. Okay, so based on these two ways, there are different methods of strengthening. The first and the simplest one is section enlargement again. So simply saying increasing the area of footing, which in turn will increase the load per unit capacity, which in turn will decrease the load acting per unit capacity of soil underneath, and this will lower the allowable load below the soil bearing capacity. So you might have went through this discussion in foundation engineering that the allowable load should be lower than the bearing capacity of the soil. Okay, allowable stress should be lower than the bearing capacity of the soil. So allowable stress can be decreased by increasing the area of footing. Okay, so figure it shows the figure below shows the same thing. So this is my old footing. Okay, so this is my old footing. Okay, and I have add like new more concrete near the old footing, and I have provided reinforcement, and I have provided shear keys also, and I have connected this new concrete with the old concrete, and I have increased the area of footing. So this is section enlargement. Here you can see dowel bars are used to connect old concrete with the new concrete properly. Okay, so here also there is connection of new concrete and old concrete, and for connecting longitudinal bar, some concrete portion was stripped from the old footing, and near that the old and the new reinforcement are connected with each other, and concreting was done. Okay, so this is how both old and new concrete are locked properly with each other. Okay, and in this images also you can see the series of activity. So there was my whole old footing in which holes were drilled throughout the members. In these holes dowels bars were inserted. Okay, then the steel reinforcement cage was installed all across the existing footing, and then concreting was done. The whole activity completion of this fourth step will provide me a enlarged footing area. Okay. The next commonly used method is underpining. So this is a process of providing new or additional foundation without disturbing the stability of the existing foundation. So in the first method, what we saw, we are like disturbing the old foundation first, and then we are enlarging the area of foundation. But in underpining, we provide additional foundation without disturbing the existing foundation. And where it can be used, okay, it can be used to strengthen shallow foundation when the structural deep foundation is erected nearby. So suppose there is my structure which has a shallow foundation. Now near the structure, new structure is to be made with which is having a deep foundation. Now due to this, my soil here will be disturbed, and my foundation here won't be able to take much load. So for strengthening such shallow foundation, I can go for underpining. Okay, or I can use underpining for protecting existing structure from excessive or differential settlement, or to enhance the bearing capacity of foundation in cases where functionality of the structure has been abrogated. Okay, now there can be different ways in which underpining can be carried out. There is pit method, there is pile method, and there is chemical method. So let's see each one of them one by one. Okay. So let's first talk about pit method of underpining. So basically this method consists of enlarging the existing foundation by removing soil from beneath the foundation, replacing it with concrete or reinforced concrete or grouting material. Okay, so here what we do, I have an existing foundation. I will remove soil from all across the existing foundation, and I will place a concrete in the pit. Okay, so what this will do, it will increase the area of footing, and this in turn will strengthen my foundation. So, an important thing here is that proper shoring shall be done to prevent any settlement. So, when I am digging the hole near the foundation, I should do proper shoring on the side so that there is no soil settlement from occurring from the side. Okay, and this is a very commonly used method for strengthening the foundation. Why? Because it is simple and cost effective. Okay, so we can see in the images also, like in the first image, a pit is dug across the footing, timber shoring is done, then an external support using needle beam and curves is provided to the column. Once there is a temporary support in place, a soil from underneath the footing is dug, and a new precast concrete foundation is placed below the old foundation. Okay, and this will strengthen my foundation. Okay. The same thing is done in the second image also. However, this time the support came from a cantilever needle beam as extending till the nearby column, using a hydraulic jack along with a hydraulic jack in between. Okay. So this is how pit method of underpining is carried out. Now, in pile method of underpining, the method consists of strengthening the existing foundation by installing piles through pre-drilled hole. and this pile increasing the load carrying capacity of the existing foundation. Okay. Now in the first method, the pit method, there can be risks of settlement from the side, but in pile method, that risk is not there. Okay. So there are several ways in which pile method can be carried out. In the first image, you can see two precast piles are being installed on either side of the column footing attached using a pile cap needle. Okay. In the second image, you can see a pit is dug from the footing side beneath the existing footing after having external support, shoring, and then underpining is done using precast concrete wall. Okay. Till a new foundation which is located in soil strata with a much higher capacity. Okay. And in the third image, you can see again for the same process has been carried out. This was for a column, this was for a wall. Okay. Several other ways of underpining are also there. Like here, you can see jack pile underpining, in which a hydraulic jack is used to drill below the existing footing till we reach a soil with a strong bearing capacity. Then, in the drilled hole, dowel bars are grouted through the holes with precast concrete jack piles in number of small pieces. Since dowel bars are connected to each other, okay, so I can install precast concrete in number of pieces. Finally, the top of the jack pile is connected to the existing footing with using a beam plate, and the top of the dowel bar is inserted to that plate, and this would cause load transfer to properly transfer from the existing concrete to the underneath soil. Okay, so you can see here a hole is drilled. Through the hole, dowel bars are inserted and they are coming till the top near the foundation. Okay. In the second image also you can see reinforced concrete needles and piles are used for existing footing by placing RC piles on the either side and connecting with the RC existing footing using a needle beam. Okay, so on both the side, reinforced concrete piles are placed and they are connected with the existing concrete, either on both the side or either on one side only, depending upon the need. Okay. In this image, you can see uh, like angle pile underpining has been carried out. So you can see at an angle, a hole is drilled until I reach a firm strata, and then in this hole, steel lining is installed and concreting is done. Okay, while here you can see in between near the existing footing a hole is dug, and inside that precast concrete is installed and that is used to support the existing column. So this is known as column underpinning. Okay. Now these are all strengthening method for footing. Another way is by increasing the consolidation of soil, and this can be done by chemical method. So what this does, it consolidates the foundation soil by employing chemicals that are driven through perforated pipes. So here you can see through pipes, chemicals are grouted inside the soil, and these chemicals will increase my consolidation of soil. If my soil consolidation will increase, the bearing capacity of the soil will increase, and it will be able to take more load from the top. So it will strengthen my foundation. Okay, so these chemicals are nothing but combination of sodium silicates and waters. Okay, I hope everyone are clear with the discussion of foundation strengthening. Any doubt? Any doubt in the discussion of foundation strengthening? Okay, so let's see some real life examples of foundation strengthening also. So there are these four cases. Try to identify the method used in each of these cases for foundation strengthening. I will wait for a couple of minutes for you guys to think, and then I will tell you the answers for each one of them. Till that time, think about the answers also. And if you have any queries in the discussion till now, write those queries also in the chat box. We'll take a like pause for 2 minutes. Okay, think about the answers. let's see the answers now. Okay, so in the first image, we can see underpining is being done. Pile method of underpining, we can say. How? Because there was existing footing. Okay. There are several cracks in the footing that was observed. Maybe since the load carrying capacity, the functionality of the house may have been increased, the load in the house. So now what was done? From beneath the footing, like through pile method, the footing was connected with the strong rock strata. Okay, so till the rock strata, the drilling was done using jack pile maybe, and then the footing was connected till the strong soil strata so that it can take more load. Okay, so here you can see in different cases how uh, till rock strata the drill was done and the existing footing was connected to that. Okay. In the second image, you can see this can be pit method of underpinning. So here you can see pit was dug across through across from all the sides of the existing footing, and a new concrete footing was provided, and it was connected to the existing footing. And from sides, here you can see it was supported from the side also, and then this will be filled with the concrete overlay to cover the whole pit. Okay, here you can see section enlargement has been done. Okay, so from sides, these are a longitudinal reinforcement, and these are like dowel bars that are connecting to the old concrete. These are foam works that are placed on the sides. So once this reinforcement cage is in place, now concreting will be done and the foam work will be removed, so it will increase the footing area. Okay, so this is by section enlargement, this is by pit method, this is by pile method, and this is chemical method. So using chemicals, they are delivered using holes, and these chemical will increase my soil bearing capacity and it will strengthen my foundation. Okay.
Sir, with respect to these all photographs, sir, what uh, basically the external columns can be addressed, external columns which are there with the foundation. How about the internal columns of the building, sir? Like, how do we reach out to that foundation and then do this underpinning oblique pit method, sir?
So basically for internal columns, we can go for directly column strengthening. If the
No, sir. No, 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 sir. The column which is resting on the foundation of the internal column, internal foundation, if we can say the center of the building or something like that, sir.
so you can use this method, na chemical grouting. This can be done for
But sir, if the extent and the damage is not known, because from external, like for example, in number two, sir, we have dug down all around the corner of the building,
hmm,
and we could make out that this much SBC or whatever calculations we get about the existing ground conditions, and then we go about the jacketing and providing extra strength to the foundation.
okay.
But the internal foundations, how do we envisage whether we can go for chemical grouting only, because it may not take that much of load, or some conditions might be there.
So for that, you must know the existing condition of soil. So what you can do, you can always calculate the soil bearing capacity. You know how much load is acting on the internal column. You know what is my bearing capacity of the soil, and these chemical methods. Uh, these methods from these method, you know how much they will consolidate the soil. So suppose they are consolidating the soil by 15% more, so you know how much my soil bearing capacity will increase, and if that increase is sufficient to take load or not. Okay, so
So that means, except this chemical grouting, we don't have any other options for the internal foundations.
if we can access the internal foundation, we can go for it. So since I talked initially also, na, when I am talking about strengthening, I will I will like disrupt the functioning of my existing structure for some time. So from inside also, we can try to like between columns, if I have space, I can get some area where from which I can access the existing footing, and if I can provide section enlargement there, that I can try.
Okay, sir.
Okay, if there is a large space between footings, then from inside also I can access those areas, no?
Yes, sir.
Okay, so Uh, as Now, as a special case of strengthening, there is one more thing that we can talk about, that is slab jacking. So, initially we saw this is nothing but like for pavement slab, how we talked initially in one of the methods of strengthening. Okay, so and in the previous session also we saw one example where there was a disoriented slab and it was repaired by grouting inside. So that method is known as slab jacking. Okay, so the slab jacking is nothing but the process of raising slab and filling the voids underneath, and it is used to level or align the slab distress which can be caused due to settlement, erosion, or flooding of underneath soil. Okay, now how slab jacking is carried out? By drilling hole in the pavement slab at the affected area, by inserting the grout material through the hole, by sealing the hole from the top after grouting, and then by resurfacing the slab with a polymer modified concrete or a normal concrete. So in the image also you can see I had a slab where there was cracking and settlement in the slab. So what we did, we drilled hole through the slab. Now I will do uh, grout. I will insert grouting material. Okay, so that I can raise the slab again to the initial level, and then I will seal the grouting material from the top, and I will resurface the slab from the top. So this is known as slab jacking. Okay. So here, these were all the methods in which repair was carried out using steel as a repair material, steel and concrete as a repair material. Okay. Now, earlier in the session, we talked about another way in which strengthening can be done, and that is using composites. So, now let's discuss what are these composites and how they are used for repair and retrofitting. So, what is a composite? A composite is nothing but a combination of two or more material at macroscopic level. Okay, one is the so in these two material, one is known as the reinforcement part and the other one is known as the matrix part. So we will ahead we will see what do we mean by reinforcement part, what do we mean by matrix part, and how they are used as a composite. So what are the key features of composites? So key features of composite are both the reinforcement part and the matrix part are different from each other. Okay, they are chemically different. They are separated by a distinct interface, and unlike concrete, these properties are anisotropic, so they can vary in all the direction. So they depend upon the orientation of reinforcement part mainly. Okay, so property depends upon the orientation, position, geometry, and amount of reinforcement part, and property depends upon the matrix properties also. So in concrete, what we say, it is a homogeneous material, it is isotropic, so in all the direction the properties are the same. But in case of composite, it is an anisotropic material, properties can vary from in different directions. Okay, and in combination, the reinforcement part and the matrix part have superior performance than the individual component. So composite is has more superior performance than the individual component, either reinforcement or matrix. Like a similar ideology to reinforced concrete. So we say concrete is strong in compression and weak in tension, and steel is strong in tension and weak in durability. So both combination of steel and concrete, reinforced concrete, is a much superior material compared to individual steel and concrete. The similar ideology can be applied here. Composite is a much stronger material compared to alone reinforcement and matrix. Okay. Now, based on the reinforcement part of the composite, a composite can be categorized into three types. Okay. These are fibrous composite, which consist of fibers as reinforcing element in matrix of another. So, like there is fiber reinforced polymer composite, there is glass fiber reinforced polymer composite that you must have heard about. There is particulate composite like concrete. Okay, so these consist of macro-sized particles as a reinforcing element in the matrix of another material. So in concrete, we have aggregates which are dispersed in cement matrix, and both of them together act as a composite. It is an isotropic composite, we can say, concrete. And third is laminate composites, so which are basically composed of two different layers of material stuck together. So these are basically formed by stacking the fibrous composite only. Okay, so we will see later on how laminates are related to composites. Okay, so the main importance here is for us to understand. Right now, the most important thing for us is to understand the fibrous composite, because particular composite is nothing like concrete, and laminate we will be able to understand after we understand the fibrous composite. Okay. Now, fibrous composites can be of different types. Okay. It can be a polymer matrix in which polymer is the fiber in the matrix of another material. It can be metal matrix in which metals are the fibers in matrix of another material. Ceramic matrix can be there and carbon matrix can be there. For each of these type, the fiber and the matrix can be of different combination, and you can see that in this table also. So as we will move along in the session and in the with the course, we would be able to identify which one we need and how to make choice, whether I need to go for polymer or ceramic. In the polymer also, what should be my fiber, what should be my matrix, each one of them we will be able to decide once we understand what is the role of fiber, what is the role of matrix, and how they contribute to the composite. Okay. Now, knowing the basics of composite and how we understand them as a combination of reinforcement part and a matrix part, let's dig deep into fiber reinforced polymer composite. Okay. So, also known as FRPC. So, FRPCs are nothing but materials, composites in which high volume of micrometer diameter fibers are reinforced within polymer resin matrix. Okay, so in this, the reinforcement part consists of fibers and the matrix part is the polymer resin. Okay, so you can see fibers can be of different types: glass, carbon, aramid, ceramic, boron. And polymer resin can be polyester resin, epoxy resin, vinyl ester resin, different types. Okay, in the images also you can see some of these FRPCs and their practical example. Like the first, you can see this is a glass fiber reinforced polymer, and it is mainly used for making sheets. Okay, FRPC sheets. So this is carbon fiber reinforced polymer, which is used for repair purpose of concrete structure. And there is aramid fiber reinforced polymer, which are used generally in thermal application for fire resisting suits. In this these are used. Now how we dictate how each one of them possess which properties, these are the material property that we will understand slowly. Okay, now if I break down FRPC to understand the importance of each component, the fiber piece of the composite. So mainly there are two main components of the composite: the reinforcement part, which is the fiber for me right now, and the matrix part, which is the resin for me. So when we talk about fiber piece of composite, the fiber face are the main load carrying component. Okay, so when I talk about a composite, my fiber face are the main load carrying component. Okay, they provide strength and stiffness. And how we identify fiber face, their length are much greater than the diameter. So if I say aspect ratio, L by D ratio, it will be ranging in the value between 10 to 100. Okay, in the table we can see different types of fiber faces and their dominating properties. Like you can see glass fiber, these are made of silica. And what are their main characteristics? They have a high elastic modulus with high strain. Okay. What are their durability properties? They are chemically inert. They have excellent insulating properties. And glass fibers comes into different types. So there are E glass which have low electrical conductivity. There are S glass which have high strength. There is A glass which have high alkali content. There is C glass which has high chemical durability. There are M glass which has high stiffness, and there are D glass which has low electric dielectric constant. So depending upon our application, we can choose any one of the type of glass fiber, and we can use it for suitable application. Then there is carbon fiber, which is made up of carbon. Its characteristics are high elastic modulus and lightweight, and it is resistant to high temperature, and they are chemically inert. So there are different types of carbon fiber like standard, high strength, high modulus, and ultra high modulus that are available depending upon the properties of carbon. Okay, there are aramid fibers which are mainly based on hydrocarbon chain. They have high elastic property, resistance to impact, fatigue, and they are lightweight. They have high moisture absorption capacity and low melting point. And there are different types like Kevlar 229, Kevlar 49, Kevlar 149. There are ceramic fibers also, which can be metallic or non-metallic oxides. They have high elastic modulus, high strength. They have durability properties like high temperature capability and high good chemical inertness. And these are based on silicon carbides and aluminum oxides. And finally, they are basalt fibers, which are made of silica, aluminum, and iron oxide. They have high tensile strength, high modulus of elasticity, and impact resistance, and they are known for their temperature resistance and chemical inertness. Okay, so each fiber have their its own characteristics, and based on those characteristics we can make a appropriate choice of fiber. Oh, okay, so similar table, a similar table can be partially understood from the stress strain profile of different fibers also. Okay, so here you can see in the stress strain profile, you can see all fibers are showing a linear elastic behavior, with glass fibers having a highest strength and strain limits, while carbon fibers are stiffer and have low ultimate stress limit. So some of these properties along with additional properties are summarized in the table also. Okay, so in this table also you can see some of the properties where you can one can see glass fibers are superior than aramid fibers in terms of aramid fiber, and compared to carbon fiber and aramid fiber, both glass fiber are superior in terms of its higher specific gravity, higher tensile strength, higher percentage elongation, and higher coefficient of thermal expansion. Okay, now, the second major component of FRPC is the polymer, or we can say the matrix part. So, polymer are nothing but the chain or network like structure made of large number of smaller units, which are known as MERS. So, MERS is nothing but smaller units. Okay, and polymers are made of a large number of smaller MER units. Okay, so they support and protect the fibers, and they are help to transfer the load to the fiber. So basically what polymers are doing, they are acting as a protective barrier between fibers and environment, and they are transferring the load to the fiber. Okay, so polymers are broadly classified into two types: thermoplastic polymer and thermosetting polymer. So by thermoplastic polymer, I mean the polymers which soften and liquefy on heating and can be reshaped in many times. So they offer advantages like high fracture toughness, chemical inertness, and pleasant appearance. While some of the disadvantages of thermoplastic polymers are high viscosity at room temperature, due to which they are difficult in mixing due to their high strain limits. Okay. Example of thermoplastic polymer are polyethylene, polyvinyl chloride, and polypropylene. While thermosetting polymers solidifies by chemical reaction, and they cannot be recycled or reshaped. Okay, they are widely used matrix in FRPC because they are easy to handle at room temperature, and they offer advantages like thermal stability and chemical resistance. So with change in temperature, their activities are not changed, so they are thermally stable and they have chemical resistance also. However, disadvantages is they have a limited storage life at low temperature and low values of strain to failure. Okay. And examples are phenolic resin, epoxy resin, and polyurethane. So this limited storage life at low temperature, one can understand from the stress strain diagram also. This is for epoxy resin. So you can see from the profile, in cold weather at 40 degree minus 40 degree temperature, epoxy resin is stiffer with higher strength, while as the temperature increases from minus 40 to 25 to 40 to 60 and then till 80 degrees Celsius, there is a drastic drop in strength and stiffness of the epoxy resin. So you can see the changes in property with temperature, how it is happening for thermosetting polymer. Okay. Similar to the discussion in fiber, these tables shows how properties of some commonly used resins compare with each other. So here we are talking about polyester, vinyl ester, epoxy, and phenolic polymers, thermosetting polymers. So like we can see, while phenolic resins have higher compressive strength. Okay, so phenolic resins have higher compressive strength. Um, Polyester resins have more thermal coefficient. Okay, and epoxy resins have higher tensile strength and elongation property. So for epoxy resin, elongation properties and tensile strength are more superior. Okay, so based on the mechanical property and some other durability properties, we can decide which one we need for our own application. Like in this table, it is shown. Like polyester, they have low cost and easy application, and they are generally used in glass fiber plastic construction industry, glass reinforced construction industry. Like vinyl ester, they have superior chemical and water resistance property, and they are used in construction and marine industries. Epoxy, they have better adhesion and resistance to degradation, and they are used in the range of industries. While phenolic polymers, they have excellent fire resistance property, and they are used in aircraft interior, ship industry, and location of public occupancy. Okay. Apart from these two main components, fibers and polymers, there can be additional components also that play an important role in FRPC. These are filler phase, which reduces cost and provide dimensional stability, and they can improve the mechanical properties also. Its examples are carbon and glass material. There are coupling agents which improve the adhesion and bonding between dissimilar phases, fibers, and matrix. Examples are aminosilanes, epoxysilanes, and methacrylic silanes. And there can be coatings which are applied to fiber to improve the wetting and facilitate better bonding along with the coupling agent. So these can be silicone coatings and acrylic coatings. Okay. Now, based on the properties of individual component, the properties of bulk FRPCs is dictated, and thus it can be said that the fiber dictate the stiffness of the FRPC, and the properties of fibers are strongly dependent upon the orientation of fibers. Okay, so for example, properties like tensile strength and modulus of elasticity are maximal along the direction of the fiber and minimum along the perpendicular direction of fiber. So that's why we say the orientation is also very important when we talk about FRPC, and thus it is an anisotropic material. And since orientation governs the FRPC and the amount of fiber and the properties of fiber and metrics govern the FRPC, the, we can tailor the properties of FRPC as per our need to meet the application demand. So we can see in the first diagram also the justification of the statement that we talked initially when we talked about composite, that was in combination a composite has superior performance than individual compounds. The same can be seen in the diagram. Fiber has higher strength and higher stiffness, while matrix has lower strength and higher percentage elongation. A combination of both composite has a decent strength as well as stiffness and elongation property. And the second image, in the second diagram, which we can see same stress strength profile for different kinds of FRPCs that we discussed really recently. So as can be seen, the number two, the S glass epoxy FRPC has the highest percentage elongation property, while my carbon epoxy polymer FRPC has the highest strength. So based on my application demand, I can tailor which material I want for the use of FRPC. Okay. So as I said recently, the orientation of fibers plays an important role in dictating the property of FRPC. So how orientation plays an important role, for that we need to understand the basic unit also. So a lamina is a combination of large number of fibers in a thin layer of matrix. Okay, a 2D in a 2D. Okay, and piling of lamina makes laminate. Okay, FRP laminates. Now if we assume fibers are oriented along for are same in fiber orientations are same in each lamina. Okay, so a laminate can be of two types. It can be unidirectional laminate or a multidirectional laminate. And you can see in the unidirectional laminate all fibers are along aligned on along the x-axis, so the strength will be maximum along the x-axis. And in multidimensional laminates there is a sequence of stacking in which I can dictate how much strength I need in each direction, and I can thereby form a multi-directional laminate. And once I'm stacking laminate over each other, I will form a FRP composite. Okay. So, due to this differential stacking of laminates and different possible orientation of fibers, the properties, mainly elastic properties, are dictated by the direction of fiber orientation. Okay. And based on this, FRPC can be said to be of three type: orthotropic, transversely isotropic, and isotropic. If my properties are varying along all the three direction, it is orthotropic. If it is varying along two direction, it is transversely isotropic, and it is if it is same along all the three direction, it is isotropic. Example of isotropic can be metal. Okay, metal is a isotropic material. Okay, so here you can see in the images also isotropic material and transversely isotropic material, how they appear, and how properties of fiber along x-axis dictates the elastic properties for different combinations of FRPC. Okay, I hope everyone are clear with this basic discussion of FRPC we had till now. I tried to summarize a massive topic here into a very simpler understanding. The content here is a lot, but just rereading the slides again and revisiting the lecture recording will make things more clear to you, and you will be able to understand in a much simplified manner. Still, if anyone has any major doubt, they can ask. Any doubts?
Sir, today are we going to solve any numerical, sir? Because in the assignments we are finding difficult the assignment 4, sir.
Basically, like the delivery of lecture is such that before submission of assignment, I can't tell you the solutions related
No,
to the
sir, not
assignment.
solutions, sir, but the same what ma'am had explained in that
So
those.
numerical we will do. Maybe not today because still we need to cover some little bit portion. But in the next live session, we'll start with the numerical.
Okay, sir.
Okay, that discussion part of numerical was very extended in the lecture recording. I will try to simplify it in a very small way, simpler way, so that everything is clear to you. Okay. Any doubt in this theory part of FRPC? What is FRPC? What are different types of fibers? How fibers properties change? What are polymers? How are different types of polymers which are present? How fiber orientation affects the property of a FRPC? And based on orientation, how we can classify FRPC? Any doubt in this question? Okay. So if no doubts, we will move ahead. I guess there is one question. Okay, so like when I make my lectures, na, I look take into account what is there in the assignment. So that numerical part, don't worry, that we will also discuss. So it will be very easy for you to solve numerical. Then I will tell you a very simplistic way how to deal with numerical and how to think for them. But all the theoretical questions that are there in assignment, once you just go through my lecture either through the PPT that is uploaded or through the recorded session, you will be able to easily answer those questions. And if still you are not able to answer any question, you can drop that question in the in the chat box. This question was a problem to me. Like in the next session, you drop that question. I was not able to solve this question. You will see that also. But just first, just go through the session because I make my session based on the how what is the level of assignment. I try to make the session one level up only so that it is clear to you. Okay. Okay, let's see ahead because there's a lot we need to discuss now and time is very limited. So now we talked how the properties of composite is affected by fiber. mainly due to the orientation of fiber. However, one more factor that is critical in defining the elastic property of a composite is the relative proportion of fiber and matrix in the composite. How to determine elastic property is what is known as micromechanics. Okay. So simply saying micromechanics is understanding the elastic property of composite at micro level based on the load sharing between fiber and matrix, which in turn is dependent upon the relative proportion. Okay, so we saw earlier that the orientation of fiber is important. Now we will talk about how the relative proportion of fiber and matrix are important, and how the property of fiber and matrix, how in combination they determine the property of a composite. Okay, now how to, since there is engineering involved here at micro level, okay, there shall be some assumptions to discard some practical vulnerabilities. And what are these assumptions? Both fibers and matrix are homogeneous and isotropic. So when I talk about fiber, there is a single type of fiber, either glass, either carbon, either aramid. And matrix, there is a single matrix only. Okay, so both fibers and matrix are homogeneous and isotropic. So right now I'm not taking into account the orientation. The orientation part we have discussed. I'm not taking. I'm right now taking into account the properties, proportions, and the properties of fiber. Okay. Fibers, matrix, and the resultant composite exhibit linear elastic behavior. So this point we have seen earlier also. Fiber and matrix both exhibit linear elastic behavior, and that is what we'll assume right now also. Fibers are uniform, regularly spaced, and perfectly aligned. So this is one assumption we'll make. Matrix is free of void, so there is no void inside the matrix. So the total volume of the composite is equal to the volume of fiber and the volume of matrix part. Okay, there is no air void inside. There is a perfect bond between matrix and fiber. So we shall assume perfect bond so that there is proper load transfer between matrix and fiber, and the lamina is in stress-free state. So when I'm talking about lamina, like a 2D arrangement of matrix and fiber, it is not experiencing any stress right now. Okay. So in the course, we saw how different elastic properties are derived. Okay, so let's see in a very simplistic way again the same thing so that you can have a better clarity. So in the course session, you saw very like distributed discussion about the properties, how properties are composite are calculated. Here we will see in a very simpler manner. Okay, so first, decoding the fractional property of composite. This is the base. Why? Because these fractional proportions will decide later the elastic property of my composite. Now, how to determine the basic property of composite, knowing how much quantity of fiber and matrix are there, is what is known as fractional proportions. Okay, so suppose I have a 2D lamina. Okay, I have fibers and I have matrix. Now, generally, fibers and matrix are homogeneous, like they are mixed properly inside a composite, but right now I'm representing them in a separate, as two separate materials so that it is simpler to understand. So suppose I have this composite. Okay, and I know how much fiber I added. So weight of fiber I know, volume of fiber I know, and for matrix part I know the weight of matrix and volume of matrix. Okay, and now I want to compute the proportion. What is my proportion of fiber, what is my proportion of matrix, and what is the density of composite. Okay, so how to do that we will see now. Okay, so I need to type now. So how I can write my volume of composite? So volume is nothing but the total volume. So you can see in the image, since there is no air void, there is only fiber and there is only matrix. So my total volume I can write as volume of fiber plus volume of matrix. Okay. Now, if I know the total volume, I can calculate volume fraction of fiber easily. How? Volume of fibers, okay, divided by the total volume of composite. So it is nothing but vf upon vc, and I know the value of vc, so I can calculate the volume fraction of fiber. Similarly, volume fraction of composite, what is volume fraction? Volume of one part upon total volumes. So it will be nothing but volume of composite matrix. Okay, volume fraction of matrix I will write here. So volume fraction of matrix will be nothing but volume of matrix upon total volume of composite. Okay, so it will be nothing but VC upon PM upon capital VC. Okay, and similarly, I can write the weight of composite. So my weight of composite, total weight of composite, I will write as WC since there are no air voids. So it is only fiber and matrix. So it will be nothing but WF by plus WM. And I can write weight fraction of fiber WF as my weight of fiber upon total weight of composite. And my weight fraction of matrix will be nothing but weight of matrix upon total weight of composite. Okay, so this is how I compute the volume fraction and the weight fraction. Very simple, knowing the weights. Now, how I can calculate the density? Okay, so I know the volume. Okay, VC is equal to VF plus VM. Okay, I know the volume fraction. Okay, now I know since there is only fiber and the like in terms of volume I need to calculate, right? So what I can do, volume, I know what is volume. Density is equal to mass upon volume. Okay, so I can write volume as mass upon density. Okay, so what I will do, instead of volume I will write it in terms of mass and density. It will become mc upon dc. So mass of composite upon density of composite is equal to mass of fiber upon density of fiber plus mass of matrix upon density of matrix. Okay, now what I will do, I will divide both the side by mass of composite. So it will become 1 upon density of composite is nothing but mass of fiber upon mass of composite is nothing but weight fraction. Okay, so it will be nothing but weight fraction of fiber upon density of fiber plus weight fraction of matrix upon density of matrix. So this is simply how can calculate the density of composite in terms of weight fraction. Okay, this is in terms of weight fraction. So if I know how much, what is the weight of fiber and what is the weight of matrix I have added and what are the properties of fiber and matrix, I can easily calculate what will be my density of composite in terms of weight fraction. Okay. Similarly, you can do here also. So I know WC is equal to WF plus WM. Okay, I will again use this relationship. Density is equal to mass upon volume. So my mass will be nothing but density into volume. So DC into VC will be equal to density of fiber into volume of fiber plus density of matrix into volume of matrix. Now I will divide both the side by volume of composite. So what will happen? The ratio of volume of fiber upon volume of composite will become my volume fraction of fiber, and the ratio of volume of matrix upon volume composite will become my volume fraction of matrix. So I will write DC will become density of fiber times volume fraction of fiber plus density of matrix time volume fraction of matrix. Okay, so in this way I can determine the density of my composite if I know either the volume fraction or the weight fraction of my fiber and the matrix part in the composite. Okay, I hope this is clear to everyone. Any doubts in this? Very basic simple calculations. Okay, if no doubts we'll move ahead. Now, how you can determine the longitudinal strength and stiffness of composite? Suppose I have a composite in which I know what is my properties of fiber and what are the properties of matrix. So I know weight fraction, volume fraction, elastic property of like stiffness of fiber, modulus of elasticity of fiber. I know stiffness of matrix, modulus of elasticity of matrix. I know what are the proportions. Now suppose on a composite I am applying a load. I want to know what is the strength of my composite and what is the stiffness of my composite. Okay, so how to determine that? So suppose I have a unidirectional composite which is stressed along longitudinal direction. So what will be my base condition here? Since my fibers are composites are acting together, the amount of strain, since they are homogeneously mixed and acting as a single unit right now, the amount of strain that is acting on the fiber and on the matrix will be the same. So what I will set, the total strain, which is written by denoted by symbol epsilon. So I will use that symbol only. Okay. So the strain of my composite given by epsilon c, okay, is nothing but is equal to the total strain that will be acting on composite due to load will be equal to the strain acting on fiber, and it will be equal to the strain acting on matrix. How? So I have applied load on my lamina or a composite. Now due to this load, there will be some deformation in the composite. Now I am assuming that there will be uniform deformation. So since there is uniform deformation, what will happen? Suppose there is like L1 elongation in the composite, the similar elongation will occur in the fiber also, and similar strain will occur in the matrix also. So the strain in the composite will be equal to strain in the fiber and the strain in the matrix. So this is my base condition. Okay. Now I know what is the relationship between stress and strain. So elasticity, modulus of elasticity is nothing but stress upon strain. Okay. This I know. And the total load taken by composite PC, so that is nothing but the load taken by fiber plus the load taken by matrix. Since there are no aeroids, so the load that is acting on composite, it will be taken by fiber and the matrix both. Now load is nothing but stress is given by load per unit area. Okay, so I can write PC in terms of stress. So how I can write? It is nothing but epsilon c. So my epsilon c, that is uh, stress acting on composite into area of composite is equal to stress acting on fiber into area of fiber plus stress acting on matrix into area of matrix. Okay, this I know. Now I know stress can be written in terms of elasticity and strain, and elasticity is a property that will be known for that we will know for fiber and matrix. Okay, so what I will do, I will write here like so this part. I will keep the LHS as the same. So sigma c into AC I can write as sigma f, that is stress in fiber, I will write as elasticity of fiber into strain of fiber into area of fiber plus elasticity of matrix part into strain in matrix part into area of matrix part. And here also sigma c I can write elasticity of composite into strain in composite. Okay. Now, since I know the strain in composite is equal to strain in fiber equal to strain in matrix, so what will happen? These three, all three terms, this, this, and this will be the same. So they will cancel out from both the side. And since I know the ratio of my area of fiber to my area of composite will be nothing but my volume fraction. Okay. Because the length is the same, the total length is the same. So A into L will be my volume, and since the length is the same, it won't matter. So F by AC will be my volume fraction only. So what I can do, I can write EC as nothing but EF times volume fraction of fiber plus EC times EM times volume fraction of composite. Okay, so you can see here how using the knowing the elastic properties of fibers and the matrix. Okay, I can calculate the elasticity of composite. Okay, now this combination where the elasticity of fiber times the volume fraction of fiber and the elasticity of matrix times the volume fraction of matrix dictates the property of composite. It is known as rule of mixtures. Okay, so depending upon the volume, I am getting the property of my composite. Okay, I hope this is clear to everyone. Any doubts in this part? Okay, once I know the EC value, I can simply write the stress also. So stress will be nothing but if I know the strain, so I can write sigma C is equal to sigma F times VF plus sigma M times VM. Okay, simple calculation. Okay, and now if I want to calculate how much load my fiber is taking, so it is nothing but PF by PC. Again I will write PF in terms of stress. Okay, so I will write PF as like this, sigma F into AF. Okay, and I will write PC as the total, this. Okay, once I know both the values, I will multiply L on the LHS and the RHS both, and I will calculate in terms of volume fraction. So what I will get, PF by PC as nothing but PF times sigma F. I can write in terms of stress. Stress I can write as elasticity into strain. Strain are same for both fiber and matrix. So from LHS and RHS they will cancel out. So it will be, we will be left with EF into VF upon EF into VF plus EM into VM. Okay, so on individual component also I can calculate what is the stress acting and what is the stress acting on the composite. And in this diagram, the same thing is shown. So suppose I know the volume fraction of my fibers in the composite, and I know what is the elasticity of fiber and what is the elasticity of my matrix part. So based on that, I can calculate my the load, how much load my fiber will be carrying in my composite, and similarly I can dictate what is my property of composite. Okay, so this was about when there is a longitudinal force acting on the composite. Similarly, we can talk about the transverse when there is transverse stress acting on the composite. So in this case, what will happen, in the transfer direction there is some load that is acting, due to which there is a deformed section. So in this case, what we say, the stress is acting uniformly on the member. Okay, so my sigma. Okay, initially we said that the strain is uniform, but in transverse direction, my stress will be uniformly across the member. Okay, so my sigma C will be equal to my sigma F will be equal to my sigma M. Okay, now what will be my total transverse displacement? It will be given by delta PC will be equal to delta TF plus delta TM. Okay, now I can write displacement. Okay, I know delta, so I can write strain. Strain is nothing but delta L upon L. Okay, so the strain in composite I can write as delta TC upon original length, that is TC in transverse direction, which is nothing but equal to delta TF plus delta Tn upon original length. Okay, Now, what I want to get this equation in terms of so that I can fit this relationship. So, what I need to do, I need to get them in terms of strain values. So, I can get how I can do that here in this relationship. Okay, I will take this relationship, I will copy this whole, and in this upper part, what I will do, just observe how the calculation is done. Okay, I will multiply by TF and I will divide by TF. Similarly, here for matrix part also, I will multiply by TM and I will divide by TM. Now, delta TF by delta TM is nothing but strain in fiber. Delta TM by TM is nothing but strain in matrix. Okay, and this whole is been divided by TC. Okay, so what my equation will become now? So my strain in composite will become equal to strain in fiber. Okay. Now my TF by total TC, since the area is the same, so TF by TC is nothing but volume fraction now. And here it will become strain of matrix times the volume fraction of matrix. Okay. So you can see how simply knowing the elongation, the strain in fiber and strain in matrix, how can I can calculate the strain in my composite. Okay, now suppose I don't know the strain in fiber and composite, I can simply write strain in terms of stress. So what I can know, I know the stress that is acting, so I can write strain as stress upon elasticity of fiber, and here the strain of matrix I can write as the stress in matrix upon elasticity of matrix, and thus I can calculate the transverse strain acting on my composite. Okay, so how the so this is how you can do the calculation, very simple. So writing strain in terms of stress, what you will get, uh, you will get the relationship sigma C upon EC is nothing but sigma m upon EF, sigma F, sorry, sigma F upon EF times volume fraction of fiber plus sigma m upon EM times volume fraction of matrix. Now, since in transfer direction, my base condition is that the stress acting on all the three members are the same, what will happen? I will have the elasticity of my composite in transverse direction written as PF volume fraction of fiber upon elasticity of fiber in transverse direction plus volume fraction of matrix upon elasticity of matrix in transverse direction. So you can see here how knowing the basic properties of fibers and matrix and their volume fraction, we can compute the elastic transfer strain in the composite. I know the elasticity of composite, I can calculate the strain in composite since I know the stress acting. Okay, so this is like here. I can paste this here. Okay, simple calculation. If you will try to understand the base condition and do the derivation on the own, you will again recall this derivation. And the similar thing is shown here, how with increasing volume fraction of fiber, my the elasticity of composite in transfer direction is changing. Okay, so as the volume fraction of fiber is increasing, I will be moving closer towards the elasticity of fiber. Okay, in transverse direction. Okay. Now another condition can be in plane shear stress. So right now we talked about longitudinal stress and transverse stress, but there can be in plane stress also. So how to deal with these conditions? So suppose I have a in plane transverse stress acting similarly along all the direction, same value acting on along all the direction. So what will be my base condition here? Tau c will be equal to tau f will be equal to tau m. So the shear stress acting on the composite will be equal to the shear stress acting on the fiber will be equal to the shear stress acting on the matrix. So the total shear deformation delta c is nothing but delta f plus delta m. Okay, now I can write delta c as gamma c times tc. Okay, I can write delta f as gamma f times tf, and I can write delta m as gamma m times tm. So rewriting this equation again, so it will be gamma c times tc, okay, is equal to gamma f times tf plus gamma m times tm. Okay, now what I can do, I will divide TC on both the side. Okay. So I can write TF by TC is nothing but my volume fraction, since my breadth and length are the same for the composite. Okay, and the fiber and the matrix, it is uniformly dispersed. So my breadth of the fiber is the same as composite. My length of the fiber, total length is the same as the composite. And similarly for matrix also. So my TF by TC will be nothing but my volume fraction now. So what will happen? Gamma C I can write as YC. Gamma C is equal to gamma F times volume fraction of fiber plus gamma M times volume fraction of matrix. So you can see how, in term knowing the shear modulus of fiber and shear modulus of matrix and knowing the volume fraction of fiber and matrix, we can calculate the shearing strain acting in the fiber. Okay, so this is the shear strain. If I know the shear strain in fiber, I can calculate the shear strain in matrix. Okay, and knowing the shear strain, if I divide it, write in terms of shear stress and modulus, shear modulus, I will get this equation. Since the shear stress and fiber, composite and matrix are the same, so it will give me 1 upon gc. The shear modulus of composite is nothing but volume fraction of fiber upon shear matrix, shear modulus of fiber plus volume fraction of matrix upon shear modulus of matrix. So simply I can write like this. Knowing the properties of matrix and fiber, I can compute the properties of composite. So in this image, you can see the similar calculation is done. Okay. As the volume fraction of fiber is increasing, this showed how the shear modulus of composite is changing, knowing that I know the shear modulus of fiber and matrix separately. So important thing is we should know the properties of fiber and the matrix. If I know the properties of fiber and the matrix and the volume of fiber and the matrix that I have, I can compute the properties of composite. Okay. Finally, we saw how we can calculate the Poisson's ratio. Poisson's ratio. So there are two Poisson's ratio: major Poisson's ratio and minor Poisson's ratio. Okay, so major Poisson's ratio relate longitudinal strain with transverse strain, and minor Poisson's ratio relate transverse strain and longitudinal strain. So what is my base condition here? I can write epsilon c as nothing but strain in transverse direction upon, for major Poisson's ratio. I can write is that okay. So Poisson's ratio I can write. I need the symbol for strain. So strain in transverse direction upon strain in longitudinal direction. So this is my major Poisson ratio. Okay. Now I know for fiber I can know what is my epsilon transfer strain in fiber. So transfer strain in fiber, okay, epsilon TF is nothing but I know the Poisson's ratio of fiber, okay, VF times epsilon CL, okay, strain in longitudinal direction we know, and similarly for matrix I know transfer strain in matrix will be nothing but the volume fraction of matrix. So this is accompanied by a negative sign, okay. So it will be nothing, not volume fraction, sorry. It will be Poisson's ratio of matrix, okay, Vm times epsilon m. So modulus of elasticity of matrix. Okay. Now I know these two conditions. I can write epsilon in terms of deflection upon length. So epsilon L is nothing but delta F on TF, and epsilon M is nothing but delta M upon TM. Okay, and I know the total deflection, total delta C is nothing but addition of delta F and delta M. Okay, so if I can write this, I can write delta C in terms of epsilon. So epsilon T into TC will be equal to epsilon TF times TF plus epsilon Tm transfer strain in matrix times the length thickness of matrix. Okay. Now, if I divide TC on both the side, I will get the volume fraction, and since this is same, okay, um, I can write this again epsilon t in terms of volume fraction and length. So finally, I will calculate the modulus. Okay. So finally, when I will calculate the modulus, it will come as Poisson's ratio of composite in longitudinal direction. It will be nothing but Poisson's ratio of fiber times the volume fraction of fiber plus Poisson's ratio of matrix times the volume fraction of matrix. So again, if I know the basic properties of matrix and I know what properties will change in what direction, I can calculate the major and the minor Poisson's ratio. Similarly, if we see minor Poisson's ratio, it will be nothing but Poisson's ratio of composite in longitudinal direction upon elasticity of composite in longitudinal direction is equal to Poisson's ratio of composite in transverse direction upon Poisson's ratio of elasticity of composite in transverse direction. So using this relationship, we can compute the minor and the major Poisson's ratio. And here you can see in the diagram how with the volume of fraction, the Poisson's ratio change. Okay. So I know this was like a bit complex and difficult to understand in first go, but try to relate the properties like what is happening, what are our assumptions, what will stay the same, and what will change, and then use the basic relationships. Once we know what we know, like before solving a numerical, you will know what are the properties of fiber and what are the properties of matrix. So what you need to do, we need to find the final relationship in which the properties of fiber and the matrix are coming, and you know the volume fraction. So you know, if you know all these things, you can compute the properties of the composite. Okay, any doubt in this part? You will try to like revisit the lecture recording and the session, you will get a better clarity on this. Please demonstrate the problem related to specific gravity, density, and elastic. That we will do. Like now it is like 8:05. 2 hours are complete. Else I would have shown you one numerical. I had a numerical prepared, but since we are out of time, then in the next session we will start with that only. So I will tell you how to read the critical values from the question and how to think ahead, how to solve the question. Okay, but for that you must know basic relationships, how you relate and how you can derive. Even if you don't remember the relationships, you should understand how you can derive. So you can see how simply in one slide I showed the derivation, whereas in the lecture you saw like three slides are used for the derivation. Here you can see simply in one slide, if you know basic condition, how load is distributing and what is changing, what is not changing, if you know all these three things, how you can compute the final relationships. Okay, any doubts in this discussion? Numerical, we'll see that you should not worry. Any doubts here? So if there are no doubts, we'll conclude the session for now. Just try to revisit the session again because it was a very deep session. It has a lot of things that was introduced new in this session. So if you will revisit the session again and you will try to understand the derivation again, it will provide you much better clarity. Okay. So yes, Dipesh, you have any doubt?
Yes, sir. Sir, how we can cover the assignment that I haven't done any assignment, but I am thinking about the registration for the examination.
That you need to concern with the NPTEL team.
Okay.
Okay, so I hope everyone are clear with the discussion of micromechanics. Okay, so this was all for today's session. Today we had first had an overview of petrograph, like we first had an overview of what is spectrographic and investigation and load testing that we discussed in the last session. Then uh, we talked about initial discussion of strengthening, how strengthening can be done. Okay, different strengthening of infrastructure. We talked about conventional strengthening techniques, that was section enlargement, post tensioning, stress reduction, and composite construction. Then we talked about different strengthening techniques that are adopted for different members of a structure, starting with beam and girder. Then we went to columns, walls, and footings. After we discussed strengthening, we talked about foundation strengthening, in which we talked about underpinning in a brief manner. Then we talked about slab jacking, and then we moved into composite, where we talked about composite, dig deep into fiber reinforced polymer composite. We understood what are fibers, what are polymers, how are different types of fibers introduced, what are the properties of different fibers, similarly for composite also. And finally, we talked about micromechanics. Okay, so this was the overview of today's discussion. Okay, thank you.